Hello, this is Dr. Liu. In this video, I will introduce you the concept of a uniform circular motion. So let's start with some simulations. Let's pop out a simulation. Okay, so here we have a simulation. There's a turntable, there's a ladybug, there's another bug. So let's put the ladybug on the turntable and start turning it. So as we can see, the ladybug is just kind of tracing this circle here, this perimeter here. Okay, so one thing we notice is there's this green arrow indicating ladybug's velocity is a vector. So in order to stay in a circular path, that velocity has to keep pointing at, let's pause here, the tangential direction of the circle, and that direction keeps changing as the ladybug travels across the whole circle. So that's one thing we observe. There's going to be a linear velocity, and this velocity keeps changing. All right, and there's also a sense that this turntable turns at a certain amount of angle per second. So that is called an angular velocity. Over here, I have a setting. This says degrees per second. So this turntable is turning 50 degrees per second. And maybe if I make it 60 degrees per second, it will take 4 seconds to rotate, right? To rotate the whole circle. So let's pause it. Let's set angle to 0, so we can return to some sort of initial position. Just ignore this velocity; it hasn't been updated yet. So as I hit play, it starts updating it. So we start here. If we cover 60 degrees per second, it'll take 9 seconds to cover the whole circle. Let's see. Whoops, what happened? Didn't like it. Okay, so let's do 60 degrees. 1, 2, 3, 4, 5, 6. Oh, that feels like it's a bit faster. Maybe the per second wasn't really working that well, but it felt like it's roughly right. So this is what the angular velocity means, is how much angle in degrees, for example, or in radians you're covering per second. And if you have a constant angular velocity, then this is what you see. You're rotating at a constant rate, and at the same time, if you're on a circular path, you will be having this constant velocity magnitude, but the direction keeps changing. Okay, so let's get back to the notes, and we'll write something down now. So for uniform circular motion, we just saw we need a constant angular velocity, and that is the this uniform part. What kind of circular motion? Uniform. So it's rotating with a uniform velocity. Now let's change this to black. I think I was using blue. So so uniform in what? In rotation. So that requires us to understand an angular velocity. So this is amount of angle per time, right? And angle could be described in degrees, radians, or any other angles, such as there's a gradient, right? There's also revolution that could describe the whole circle, right? So let's list the revolution. Right, revolution. So you can say revolutions per minute, RPM. That's pretty typical for rotating objects such as an engine. Radians per second is used in science and engineering very often. And degrees per second are easy to understand because most people understand degrees since they're in grade school. But degrees per second has some disadvantages I explained in a video that explained to you what is a reading and how do we use a reading. What's the advantage of using a reading? Okay, so now with angular velocity, we could have degrees per second or radians per second, or maybe revolutions per second or revolutions per minute. Right, so there are several different units. You can convert them into each other. I will just focus on one at a time, the degree per second. So if this value is constant, say you cover 60 degrees per second, then you have a uniform angular velocity. And the angular velocity, we use this symbol omega. So that's a Greek letter, omega. It's kind of a curly W. And that's actually a lowercase. The uppercase would be something like, looks like this. Right? So we don't really need that. Let's get rid of that. So that's angular velocity. So the uniform part does that. And then there's also a circular motion, right? So let's see what that tells us, circular. So that says something about radius, right? So we have a radius that is constant. If we didn't have a constant radius, say the ladybug, that would probably be spun out. If there's not enough friction, the ladybug couldn't hang on to the turntable, right? The radius wouldn't be constant. It wouldn't be a circular path. It would be some sort of spiral, right? So a constant radius, let's call that radius r, and we'll have that in meters. That's easy, right? So now we already have established two quantities, an angular velocity and also a radius. We also had a linear velocity. So let's see, we have a linear velocity. And this linear velocity is v in meters per second. And we saw how that behaves, right? The linear velocity has a constant magnitude, constant v, that is magnitude. But direction changes, right? So the direction change, I'll just remind the audience, if you're here traveling counterclockwise, you'll be moving with this velocity v. If you're here, you'll be moving with this velocity v, although you have the same exact lengths. You'll say you'll be doing that, velocity v. Maybe here, this velocity v. Even maybe add another one, velocity v. So you'll be going around with the same exact magnitude. That means you'll be covering the same amount of arc distance per second, meters per second, also measured arc distance. So that's what you're doing in your uniform circular motion. And the next thing we want to do is to see how the v and the omega are related, because we have two bugs. I don't know if the other one's a dung bug. So we'll place the other bug on the turntable and see how that bug fares with the ladybug. So let's bring back the simulation. Okay, so we have a simulation here. This gray region, this is kind of 1 unit of radius, and the blue region another unit of radius, and the green region another unit of radius. This kind of faded orange color, red, is another unit of radius. So at the moment, the ladybug is 1 unit, 2 units of radius away from the center. So this bug, okay, let's see, let's pause. Okay, let's put this bug, can I actually pause? Maybe I'll reset it. So okay, ladybug's still here. We'll put this this maybe down below right here. So 1 unit, 2 units for ladybug, 2 units, 4 units of radius for that other bug. So let's play, and we'll have a 60 degrees per second rotation. Let's get that started. Okay. So that looks like, if I pause it, okay. So ladybug has this much velocity back there, the length, and this other beetle bug has basically 2. so twice as much. It's hard to see that, but this magnitude is actually twice as big. So maybe we can increase that to an even faster speed. See if that is even doable with this simulation. Wow, look at that. That's very fast. So 1 rotation per second. Let's pause. Okay, so this is a more convenient way to describe the relative magnitude. You can see this length here that kind of extends over here, and there's another unit of that length as a velocity. So to think about this is not too hard to think about it. Both bugs have to complete the same exact amount of angles per second, and right now it's a whole circle per second. So both bugs have to complete the whole circle per second, and the ladybug is closer to the center, so the radius is less and the circumference is less. And here this other bug, maybe it's a dung beetle, I really am not familiar. So the radius is twice as large, so the circumference is also twice as large. To think about that, you have to cover twice the circumference if you're twice the distance away in order to stay in sync with the same exact rotation per second. Right? That makes sense. Your velocity, linear velocity, will be proportional to where you are at compared to the center. So let's get back to the notes. So with the linear velocity, because we're covering this circumference, so say S circumference is equal to 2 pi times r, right? And the velocity is basically how much arc distance you're covering per second. So this S over time. So it is, let's move that up, 2 pi r over t, right? And we know that this t is actually a period, right? A whole period we were describing. So this thing is the angle per second. If we're using radians, right? 2 pi radians, that's a full circle. That's 1 revolution, right? Or 360 degrees. So that much angle over this total period, that should tell us how many radians per second, or if you convert in degrees, how many degrees per second, right? So this is the angular velocity portion, and if you look here, the velocity has that factor 2 pi over t, and then this r, if you factor it out, this is angular velocity. So angular velocity times radius equals linear velocity. So what that means is if you have a constant, so if omega is constant, then the velocity will be proportional to the radius. So if you're twice as far away, then you'll have twice as high velocity to cover twice the circumference. And that also means if you're standing at the center, then you shouldn't have any linear velocity. Although you're still turning around yourself, you don't have any linear velocity. So let's place one of the bugs at the center. Oh my goodness. Okay, yeah, the bug is getting pretty just confused what's going on, maybe dizzy at the same time. But there's no velocity right there. Okay, so let's pause it. No need to cover any circumference, no need to do any arc distance, right? So no linear velocity. So let's get back over here. So now we have the basic ingredients of uniform circular motion. There's these things, the angular velocity and linear velocity, and also a radius. You could also have this t period if you want. This is the time it takes to complete one full circle, and I know that period is equal to how fast you're turning and the time, basically the let's do this, how many radians over how fast you're turning. And period can also be equal to what is the arc distance and how fast are you covering those arc distances, right? So even from here, you can find a relationship between omega and v is omega times r is equal to v, but we won't be doing that. So anyway, we have a number of parameters that describe uniform circular motion. And now let's introduce one last one, which is the acceleration. We call it centripetal. Centripetal acceleration. So this is still a, and it's meters per second squared, and sometimes written as ACEN. So I want to see how that is related to the rest of the parameters. So let's bring up the simulator. Okay, so I haven't really displayed any acceleration vectors. Let's display it. Oh, look at that. So oh, that's right, because this is really fast. So let's do 60. Okay, so might be a little too slow to display that vector now. Okay, so let's do 180. Alright, so that means 1 full rotation per second. And let's pause. As we can see, the velocity is a little less because we don't have to go that fast. And then there's this acceleration that points constantly toward the center. So what's the reason for that? Well, if you think about this, see, I can move. Ooh, okay, that's actually a manual operation, so I don't want to mess with that. So 180. Let's 180. Okay, so let's pause so we can step through this. So right now the ladybug is right here. The velocity points to the left mostly, a bit downward. And next step, it is a bit more downward. Next step, bit more downward, right? The velocity keeps going a bit more downward until it's almost entirely downward and then down to the right, correct? So this would require some change in velocity in order to make it happen. So when you have the velocity down to the right slightly, and then the next time you have down further to the right, so you'll require some change of velocity in about this direction I'm pointing, which is along that direction of acceleration. And the acceleration will be related to the velocity. Is it proportional to the velocity? That's a good question. So it's actually it's easy to see if you just play this. See, the acceleration points almost all the way toward the center, so that's how long this vector acceleration is, right? So that's for 180. So what if I double? If I double the angular velocity, will that red arrow double? That means getting across to this point or even more. So let's give that a try. 360, that's doubling the angular velocity, and let's play that. Okay, so definitely not really twice as long, right? The vector was pointing to about this point, and if it's twice, if it doubles, and when the velocity, average angular velocity doubles, it would be about here. But this is about 4 times as long. Okay. So, well, I have this ruler I can try, but this ruler is probably hard to use. It doesn't seem to rotate, right? So that's okay. So what we just learned about was there's an acceleration. This acceleration points toward the center. In order to, let's get back here, in order to change the velocity, right? The velocity is up and then it's up to the left. So you would require some sort of leftward acceleration or change in velocity. So the acceleration will point this way. Right? So if you go from this direction to that direction, you would need some change in velocity in that direction, so you would need that acceleration. Same thing for the rest of those. Okay, so this is equal to omega squared times r. As we observe, the angular velocity doubling will not just double the centrifugal acceleration, it actually quadruples, although we couldn't really prove, well, numerically. It's more or less conceptually. We do have a lab for that. And because of the relationship between the omega and the v, right, that's how they're related, we can rewrite it as v squared over r. So we have a few different scenarios we can play. For example, if r is a constant, okay, if r is a constant, and then if you say omega goes to twice omega, if you double the angular velocity, the twice will actually get squared into 4 times. So the centripetal acceleration will go to 4 times the centripetal acceleration, right? And that's the same thing if you had, let's say, if then. Let's move that a bit further down so we can write then. Okay, what other scenario? If velocity goes to twice the velocity, and then you can use this equation, having a constant radius, so that doubles, and double squares quadruple again, so the centripetal acceleration also quadruples. So what about if you change something else? If you maintain another constant, say omega being constant, this means you're on the turntable. Something is turning at a constant speed. You can't control that. What if you walk towards the edge of the turntable, or walk towards the center of the turntable, right? So I can imagine a radius increase to twice radius. So you're basically walking to almost the edge of the turntable. You're increasing your radius, getting further away from the center. So imagine that if this is constant, and doubling that, this will double, right? Because these two are proportional. I think I forgot to write then. Okay, so I can also say something like this. Well, if your radius were to say, let me think about another scenario. So constant angular velocity. Let's say we have a constant speed. So constant linear speed. So what happens over here? Well, we could be driving a car. So we're driving a car maybe on race tracks. So we could change the tracks to get closer to the center of the radius or further away from the center of the radius, but we just maintain the same amount of speed on the speedometer. Right? That's doable. Right? So we have this maintained. That means if r were to go to 2r, that means we're changing lanes to the outer lanes, right? So then if this doubles, this actually becomes half, right? So centripetal becomes only half the original centripetal, right? You could also say, well, if that halves, then the other quantity will double, and that same thing over here. So conceptually, this can tell you what happens if you have one of those things as constant, and then you play out some scenarios, and now you realize there are actually 3 things involved: acceleration, velocity, radius, or acceleration and angular velocity, radius. So this equation here will be what we're using to find acceleration if the other 2 things were given, or find velocity if the other 2 things were given, or maybe find radius. These 2 are not exactly the same, they're related. Let's put this in here. V equals omega r, we know that. So this means you either know v or you know omega, then you actually know both if you know r. Anyway, so this will be the main equation we're using for angular for centripetal acceleration. Thank you.